Hello, this is the example for flexural bending stress. I believe Alan asked this question in on discussion board. So here we go. We have a I wide flange and have a shear force 20 kilonewton that's given. They ask us what's a shear stress. By the way, correction for my earlier comments. This is not about bending stress. This is about shear stress due to bending. Okay. So determine the shear stress on the web at A. And so how do we do that? First of all, I have the solution here, and this might be a little confusing for calculating the moment of inertia. So they have this I here. Just quick recap. When we trying to calculate the shear stress due to bending, we have tau. Tau is going to be equal to the shear force times Q, that is moment of area, then divided by moment of inertia, and then divided by the thickness at a point of interest. So since this is shears, force is given, V is given, and then we needed to figure out the Q, we also need to figure out the I. So let's first look at moment of inertia, I. And this moment of inertia, I'm going to make a comment. It's going to be regarding its neutral axis, which is at centroid. And since it's symmetric, it's right in the middle. So how do we figure out this moment of inertia rotating about this neutral axis? There are a couple of ways to do. And first thing you were thinking, oh, this I shape is made of those three rectangles. There's one in the middle, and there are two at the flanges, one in the web. So if I'm gonna divide this to 1, 2, 3, we'll have those three shapes. And now let's think about it. The neutral axis is right in the middle. And if I were using this method, I have to figure out I1 plus I2 plus I3, right? And now let's take a look at I1, I3. I1 and I3, if I isolate it out, this is 1 and the neutral axis is here. So we have to figure out this shape 1 rotating about NA. So if I were using this method, I have to use parallel axis theorem. So for example, if this is 200 and this is 20, and the distance, I'm going to use a different color, from the centroid of that shape to the neutral axis, that's going to be our D. And I believe this is 300 plus half of the 20, so it will be 150, right? Half of 300 plus 10. Okay, so that's going to be the distance. So again, if we were trying to find this I1, we know I1 is going to be equal to I3 since they're symmetric. That's going to be using parallel axis theorem. Parallel axis theorem is going to be I of this shape itself regarding its own centroid. That's going to be 112 and 200 times 20 cube, right? And then we're going to use parallel axis theorem. The shape area will be 200 times 20, then times the distance between this shape of own centroid to this new parallel axis, which is 160 squared. So that's something we needed to do. That's I1 and I3. And of course, when we're trying to find I2, it's just going to be this shape. And if you look at I2 and the axis you are trying to rotating about, it's happened to be its own central axis. So in that situation, it's going to be just 112. And now let's put our dimension here. This is 20, the thickness, and the height here is 300. So it will be 112 times 20 times 300 cube, right? So if we were using this method, then we're going to add all those together. Then that's going to be our INA. However, the solution is not using that way, but I encourage you go ahead and solve this using this method, and you will get one answer. Now let's look at how solution figure it out. Solution, they are still looking at this I shape, but they are not looking at adding those three shapes together. They are basically looking at this entire rectangle minus this 2 area here, right? So this is the 2 area I'm looking at. Then they get our moment of inertia. But the beauty of doing this is, if look at this entire rectangle. If I look at this entire rectangle, this orange rectangle, and the centroid is happen to be at neutral axis, so I don't need to use parallel axis theorem. The same thing for this 2 rectangle right here. Their neutral axis happen to be at their own centroid. Again, no need for parallel axis theorem. So that's the beauty. That's a very clever way to arrange this shape in this way. So let's take a quick look. How can we figure this out really quickly? This is 200, and the height is 300 in the web, and 20 for the flange, so will be 340. Then for this 2 rectangle right here, let's take a look. It's basically right here, right? And then let's think about the height is gonna be 300, and then we're gonna figure out the width here. So this entire is 200, and this thickness is 20. So I'm gonna use 200 minus 20. Then there are 2 rectangles here. I can potentially divide by 2. And another way, actually, I'm going to combine these 2 rectangles to be one shape together. So this rectangle, I'm going to combine these 2 rectangles together. So they're going to add together to be 200 minus 20. Right? Okay. So knowing that, our moment of inertia, this I, is going to become this big rectangle. So it's going to be 112, 200 times 340 cube. The minus these 2 rectangles together, they have a combined width of 200 minus 20. So that's going to be 112, 180 times 300 cube. And I believe if you compare this one with what they have over here, it's the same number except they changed to meter, right? Here you are keeping same as millimeter. So that's how they get their moment of inertia. So personally, I think this method number 2 is very clever. That avoids the parallel axis theorem. Okay, now I'm going to just continue. So go back to this governing equation. You know the I now. You just need to figure out the Q. Q is the moment of area, and it's asking at point A. Let's do a quick review on that one. Remember, when we find a Q at a particular point, this is at A, it's going to be the area out from point of interest. So that's going to be this area, and we're going to times the distance. That distance is that centroid of this shape, denoted as this red dot, to the neutral axis. So it's going to be from there to the neutral axis. That's going to be our Q. Okay, so QA is going to be equal to this area, which is 200 times 20. 200 times 20, and then times this y. The distance is going to be 300 divided by 2, half of that, then plus the half of this height, so it will be 20 divided by 2. That gives us 160. So times 160. All right, that's compare this one with that. It's essentially the same. Again, the unit we keep as millimeter. Then the T, the last thing in the equation is T. T is the thickness at that point, and the T is at this. That's gonna be the thickness, which will be 20. That's how they use for 20. All right, put it all together, you get your shear stress. All right, I'll see you at the next one. Hopefully this clarifies some of the confusion about moment of inertia. All right, bye now.